But what can we do without this additional hypothesis? If we do not have this additional hypothesis, we can do the following. Let us do one more step to the left-hand side. Notice that the last line of the left-hand side, if we apply the left invariance of mu, which is already given in the hypothesis of this uniqueness theorem, we got here f of yx instead of xy in here. So this is by the fact that mu is left invariant. And now we compare this with the right hand side. We see a beautiful symmetry in this comparison, namely this part. What we are going to do next is that we're going to take the difference between left hand side and right hand side. And we will think very, very hard how to make that difference as small as possible. And now let's take the difference and see what happens. When you take the difference and the absolute value, so let me just copy down everything. We can magnify this part by putting the absolute value sign inside. And let's do one more step. Let's pull this h of y outside of this inner integral. The next thing we want to do is that we want to make this part, this integral inside, uniformly small. With respect to y. It might not be uniformly small for any y. So we may have to make a compromise that to make this thing uniformly small for the y in some restricted domain. And to this end, we're going to focus on this difference, this absolute value. Notice that this difference, we can split this by the triangular inequality into two parts. F of yx minus f of x plus f of x minus f of xy. Two parts. This part can be uniformly small by the left uniform continuity of f. And this part can be small by the right uniform continuity of f. Because f, remember, f is in CC plus of G. And by our lemma 2a, so the relevant lemma is lemma 2a. Which states that any function in CCG is also uniformly continuous. Now, thanks to our lemma 2a, we can do the following. First, we fix a compact symmetric neighborhood V0 of E. Using notations, V0 is equal to V0 inverse compact. And second, because of our lemma 2a, the uniform continuity for any epsilon greater than 0, there exists a compact neighborhood V sub epsilon f containing the identity element. Symmetric. So in topological groups, we always want to make the neighborhoods around the identity symmetric for convenience. You never know when you're going to use this property. So it doesn't hurt to make every neighborhood around the identity symmetric. Compact and symmetric neighborhood, let's use notation V sub epsilon comma f, the identity. That is also contained in V0. This is not the end yet. Such that if we can make this neighborhood small enough by the lemma 2a, the uniform continuity, we can make both of those two parts small. In particular, we can make both of them less than half epsilon, such that the above is less than epsilon divided by 2 plus epsilon divided by 2, which is epsilon. For any y in V sub epsilon f, which is contained in V0. So you may want to go over this again to see if you really understand what we have been doing here. And you may wonder why we are doing this in two steps. What's the point of first taking this V0 and then taking another neighborhood of identity inside this V0? I will tell you later. At this point, it's basically because this V0 is like something fixed, but this V sub epsilon f is something that depends on epsilon and f. That's the point. But you will see later why we made this choice. Okay, now let's move on. Now we define f sub y of x as a thing inside this f sub value notation, namely f of yx minus f of xy. For any fixed y in V0, And now we look at the support of f sub y. We claim the support of this is contained in v naught times the support of f union the support of f times v naught, where v naught is this fixed neighborhood of E. Let's check this. Indeed, if f of yx is non-zero, then yx must be in the support of f. And if f of xy is not zero, then xy must be in the support of f. So if f sub y of x is not zero, then at least one of those two things must happen. Either x is in y inverse times the support of f, which is contained in, remember, we restricted y to the set v naught, so it is in v naught inverse times the support of f. But remember, we took v naught to be symmetric, so this guy is really equal to just v naught times the support of f. Either this happens, or x in the second case is in the support of f times y inverse. This guy is contained in support of f times v naught inverse, which again is equal to the support of f times v naught because of symmetry of v naught. So the support of f sub y is contained in the union of those two things. But this right hand side, this union of two products, is compact. Why is it compact? It's compact because v naught was assumed to be compact, and support of f is also compact because f is in CC plus of G, and the product of two compact sets is compact because of continuity of the multiplication map in topological groups. And the union of two compact sets is again compact. So this is compact. And hence, of finite Radon measure. The Radon measure of a compact set is finite, by definition. At this point, let me remind you of something. Remember at the beginning, when we were talking about the idea of the proof for the uniqueness part of Haar measure, I said we are going to choose this H very carefully so that we can prove for any f in CC plus of G, this quotient with respect to f is same as this quotient with respect to h. Back then, we do not have much idea of how to choose this h, except for just making it symmetric. But now I can tell you, we know how to choose this h now, thanks to our effort in here. In particular, our effort in making choices of this v sub epsilon f and v naught. So now let me tell you how to finalize our choice of h in CC plus of g. We'll construct this h as follows. First, we choose h naught in CC plus of g such that the support of h naught is contained in v sub epsilon comma f, which is equal to its inverse. Because remember, this neighborhood of identity was taken to be symmetric. Every neighborhood identity should be taken as a symmetric neighborhood for later use. And of course, this is due to the Eurozone lemma. Now, we take h to be h naught of x plus h naught of x inverse to make it symmetric. Then, the support of h will be contained in the union of the support of the first guy and the support of the second guy, which is contained in v sub epsilon f union v sub epsilon f inverse. But this guy is symmetric, so they're actually the same, which is again contained in v naught by our choice of this. Now we are ready to finish the proof. I can't wait to see it. It follows that for given f, h, mu, and nu, for the given four things, if you look at the difference between the left hand side and the right hand side, remember this is less than or equal to this guy. Now we're going to show that this thing could be arbitrarily small. The first observation is that because h has a support contained in v sub epsilon f, we can restrict the outer integration to v sub epsilon f. And now let's look at the thing inside this red bracket. Remember, if y is in v sub epsilon f, then this epsilon value will be less than epsilon. By our discussion in here, this epsilon value is less than epsilon for any y in here. That is why we want to restrict the domain of the integration of the outer integral to this small neighborhood of the identity. we want to make this absolute value smaller than epsilon. And now if you look at this function, remember this function was called f sub y of x. It has a support. Do you remember its support? The support of this function is contained in this guy. We check this. So the thing in this red bracket will be bounded by epsilon times mu of the set that contains the support of f sub y. This guy. Of course, here we are using the fact that this v sub epsilon f is contained in v naught. And when we consider this function, we also only consider the case when y is inside v naught. But here y is inside something even smaller than v naught, so we are good. We are giving this a very generous bound. That's good. So this whole thing will be bounded by this guy times the integral of h against nu over v naught. V naught is fixed. This is not fixed, but v naught is fixed. And v naught contains this. But anyway, we only need the fact that this is a finite number. So this part is a finite fixed number for fixed f, h, mu, nu. The measure of this is finite because mu is Radon measure, and this guy, remember, we showed this guy is compact. So this is finite. This is also finite because h is compactly supported and continuous. Now, let epsilon go to 0. We have left hand side must be equal to right hand side. This finishes the proof of the uniqueness of Haar measure. Because remember, left hand side equal to right hand side means that we can establish this equality, which will give us the equivalence of those two quotients for this fixed h and any f in CC plus G. So we get that this quotient is independent of the choice of f in CC plus G. And if this quotient is equal to the constant c, then for this constant c, mu is the c multiple of nu. And this verifies the uniqueness of Haar measure. And of course, as I said earlier, you need to go through also the end of the proof for the existence of Haar measure and use the approximation method with Urson's lemma and the monotone convergence theorem to get from this integral to measures. But I consider that as a routine job in real analysis. You should be able to do it yourself, But if you don't, just go back and look at the end of my proof for the existence of Haar measures. And you will see this immediately. You probably don't even bother to do it yourself. But anyway, we have proved the uniqueness. We are done.